turn off transcription. Okay. In the today, so we have I remember there's a 4-lecture Armist. I will try to post the videos as soon as I can. Today we will first reveal what we have been talking about last time, and let's start from here. So last time we talked about array and nested array, and how that sits in your memory. Basically, we use a continuous memory space to hold this array. And we talk about how to geolocate or to figure out the address of a certain item. Here is an example. Let's quickly review. Let's talk about the integer. For integer, we first figure out what is the element size. That is size for each, because the integer, so we element size is 4. Let's see, we want to look at C3. So let's see, this is C0, C1, C2, C3. Okay, let me do that. Let's assume this is C0, C1, C2, and C3. And the starting address of it, let's assume it's XC. And we can know that because each element have size of 4 bytes. If we want to look at the next address, it will be XC plus 4. If you look at C2, the address of it, it will be XC plus 8. So we can make a generalization. It will be XC. If we talk about CI, it will be XC plus I times 4 plus I times 4. That's how we geolocate the element CI. And also we talk about pointer arithmetic. If we have an integer array E with size 10, if we write down E directly in C, that is the integer pointer. If we specify which element, that will be EI. That is the integer. For each of the element, we can get the address of it, and it's an integer pointer. We can plus a number or so, and then from here we needed to put down the scalar of it. If we try to do arithmetic, this one you can suppose this is the EI, the address. Here, if you just have E, that is equal to E0, get the address, and to do the arithmetic, we will just find the index of it, and it should be I. This is when you do arithmetic between two integer pointers. And also we talk about the reverse engineering part. The way we can do this is we first of all figure out this RBP minus 48, this is A0. This space is holding 0. And the RBP minus 32, this is holding A4. After we know that, we can use the equation. Let's assume the starting address of the array is XA. We want to look at the address of A4. So we have index 4 times the size of each element. It should be the address of A4. because A4 we already know the address RBP minus 32, and we also know XA, the starting address of this array, is the address of A0. So we actually know that here this is A0. We can put down RBP minus 48. If we figure out this, we could get RBP off, move this 48 to the right side. We would have 4 times S equals 16. So we can know that S is 4. We figure out the size of the element should be 4, and we can figure out the type. It should be an integer. This is the way we solve this question. And also we continue to talk about nested array. Nested array is something we have like this: 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the matrix. And for the matrix, we need to use one-dimensional memory to store two-dimensional data structure. So what we do is we find the memory. This is starting address of it, XA. What we do is we first store the first row, 1, 2, 3, then continue to store the second row, 4, 5, 6. This is how we store a matrix. And because you can see the first row in here, it's just like the first subarray, and we use A0 to denote it. The second one is A1, so it's a array of subarrays, or we call nested array. For the nested array, we also talk about the equations. We can geolocate them. So we still take this as an example. So if you want to look at, in our example, we want to look at A3, 1. First of all, we have the starting address. We want to look at its address. Then we have the starting address of it. We will continue to look at how we locate A3. If we want to locate A3, we need to figure out what is the size for each subarray or each row of the matrix. That should be C. That is numbers of columns, and times the size. This is gonna be the size for each subarray, and because we have 3 subarrays in front A3, A0, A1, A2. We have 3 subarrays in front. So what we need to do is times 3 right here, or I, if you like. Here's I, here's J, and by this we can locate A3. After we locate A3, we would continue to locate A3, 1. So A3, 1, we got one extra element to skip. The size of it again is C, the L. So by using this equation, we can locate the A3, 1. So this is the equation is universal. If you want to look at using I and J, there is the expression. And also we did a reverse engineering. You can figure out RBP minus 1208 is A00. RBP minus 122 is A43. and then you can use the equation here to figure out the size of each element. And today we will continue to talk about struct. Before we talk about struct, do you have any questions? Oh, sorry. A question from Dino. So the rest of the class is online, but the final is in person. Yes, that's right. We will have the finals in person. Another question from Kelsey. Will we have the option of taking the final online? We should be able to do. We should be able to do that. We need a. Okay, let's do this way. If you have if you have any specific needs to take the finals online, you can email me and I can try to accommodate online. Otherwise, we would do that in person. Another question from Dino, and is it going to be open note? If not, we will do a review. We will. Okay, so we will do open book, and we also will have a review. Yeah, we will make that open book. So open book is always good news, bad news, but it will be open book. And here, let's look at what is assembly's way to handle struct. Here is the example. We make a struct. We have integer I, j, and the integer array with 3 elements, and lastly is integer pointer. And if we look at the memory space holding it, you can find that we just place each item continuously, and that's it. That's assembly way of dealing with struct. But we also need to figure out where is each element. What is address? Previously, you can see for the assembly, as long as we can figure out the address of it, then we encounter no trouble using nested array. So here, if we want to use a struct, we also need this. We need to able to find the address of one item. And take this as an example. If we look at the integer I, you can see that it will be the address or offset with 0. We can x rack plus 0. Then this will be the address of I. And based on here, you can find the address of j, which will be x rack plus 4. And if you look at the A0, the first element of the integer array, that will be x rack plus 8, so on and so on. And something different from array is that we cannot come up with a mathematical equation because each element or each item may have different sizes. There's no generic rule that we can come up with the equation and do that way. We need to count manually. That's a different part. This is what it looks like in memory for our struct. And here's the example. If we want to look at, let's see, R is the struct's pointer. And if we look at A1, you can continue to do this. A1, you have RRAC plus 12 as its address. And here is an example in the how it is used. This is assembly code using the struct, and the definition of the struct is right here. The struct name is ELE. We have one long variable, and also we keep a struct pointer, and we try to develop a function fun, and fun is right here. The assembly code is right here, and we're trying to see what is C code for the fun. And let's do it together and assume that PTR is in RDI. So PTR is a pointer, the first parameter. We know the first parameter comes in the RDI, so it's quite consistent with what we have talked about. RDI holding the first parameter. And if we look at the fun, we want to reverse engineering it. We can look at here. It seems like we move 0 to EAX. We can draw here. We have EAX, which put 0 in it, and we jump to L2. L2 is testing RDI with RDI itself. We talk about this, is trying to figure out whether RDI equals to 0. If not equals to 0, we jump back to L3. So if not equal, we jump back to L3. And do it again. And quickly, we can see that this is a while loop, right? We have a while loop, and inside of the while loop, the condition of the while loop is to testing whether PTR, this is pointer, equals to 0. If the PTR doesn't equal to 0, and then not equal stands, and we should jump back. So not equal to 0 should be the condition. And after we figure out what is the condition to continue, we can look at what is inside of the this while loop. And first of all, we add something to RAX and move 8 to some places. So seems like RAX is used as a variable, I would imagine. So let's just say here's a variable A. Here we'll use RAX. Let's assume there's a long A. We make it to be 0 in front. So right now, let me give you 2 minutes, and you can try to figure out what should be the C codes inside, or how to reverse engineering this blue square. I will give you 2 minutes. And about pop quiz, we will find time to give you the answers and go through it. Yeah, it will happen. Okay, how are we reverse engineering this blue box? What is this blue box is trying to do? Any clue you can put down in the chat window if you like. How to reverse engineering this blue box? Okay, great. Brandon, that's right. So we need to figure out what is in the RDI right now is PTR. So we have the PTR and trying to find what is inside of it. Let me clear this a little bit. So let's look at RDI. So let's draw here. RDI is having PTR, which is struct pointer. And for this struct, you can see we have 8 bytes to continue V, and another 8 bytes continue pointer P. So this is 8 bytes. This is another 8 bytes. If we talk about PTR and get its address, if we talk about PTR and we find the memory place, this RDI in the parentheses, it will be denote this V. And the RDI plus 8, here's we talk about here, it's PTR plus 8. Actually, it's not PTR plus 8. It is plus 8. Let's just see the 8 offset. RDI plus 8, this will denote P. So we can know that we would have A plus equal to PTR find the V, right? We want to add the value of V to an accumulator A. In the second step, we want to initialize the PTR, not initialize, update PTR to be the PTR point P. That will be the two lines we are trying to deal with. Any questions about this reverse engineering? And I have another question for you. Let me see. Let me write down this this structure. Let's see. I write down 3 such structure, and here is 1, 2, 3. There is a pointer. Let's see. This is the PTR. Now let's assume we have 3 such struct, and they are having 1, 2, 3 in the place, and I initialize the struct pointer like this, and the head of it is PTR, and I give this PTR to our function fun. What will be the return value? Okay, great, Brandon, that's right. The return value will be 6, 1 plus 2 plus 3. And this structure is called the linked list. I don't know whether you you know this linked list. Did you go through it in your C class? Okay, great. So the linked list is a struct like this. Usually we have one place to hold the value, and another place, this is to set up the pointer. This pointer will guide us to the next struct. So in the next struct, we have the number 2 in it, and we also have a pointer afterwards. This pointer will guide us to the next struct, which have 3 as a value, and usually it will terminate with NULL as a pointer. So this is a double, this is a linked list. And if we look at the assembly code, it usually looks like this. Okay. And we will continue to talk about the union. Union have similar definition with struct. Here we, instead of the bracket, everything is the same. We have char-C, integer array, and then a double. The only difference comes to the keyword struct and the union. And for struct and union, the difference is struct for each of these items, they coexist. So you can see this yellow is char-C, this green is the integer array, and this blue part is the double V. So they coexist. You may wonder what's going on with this blank space. We will talk about why we have blank spaces in between shortly. But let's just note that for the struct, every item, they coexist. This is the struct. But if we look at a union, in here we have one char, one integer array, one double. We actually have the same space. This is space. We either interpret this space to be C or char, or interpret this space to be we interpret this space to be integer array, or we interpret this space to be double V. So they actually the same space. We just have one space. It just depends on how we want to interpret this space. It could be either C or I2 or V, but they cannot be true all the time because we just have they shared this space. And this is the union. For union, we have to decide what is the size of it for this blue box. What is size of it, right? One thing clear is the size of it can't be the char, which is 1 byte. Otherwise, it will not be big enough to contain for the integer array and the double. Actually, the size of this union is decided by the largest item. So the first one, char C is 1 byte, and the integer array is 8 bytes in total. And for the double, it is also 8 bytes. So we decided this union should be 8 bytes. It is the largest size of the element, possible item. In the this is 8 bytes. So again, union, we can either pick up one of them, but they cannot coexist. This is union. And you may wonder why we needed some structure like this. For the union, one good example why union is helpful is like this. Here is the tree structure. You can find that in this tree structure, we have some nodes, like number 1, it has the left child and the right child. This is how we call it has the left and the right. If you look at this tree node, usually it is a structure like this. We will have 2 pointers in front. These are 2 pointers. The first pointer points to the left node. The right pointers point to the right node, and here is some data after it. So this is usually a tree structure like this. We use the pointers to point to the left node, or the right pointers to point to the right node, and then sometimes we have the data structure. And here's a node that is having the children, but you may notice some of the nodes they don't even have a child. We call this leaf. In many cases, in computer science application, we sometimes store data, particularly at this leaf node. We give data to this leaf node, and for the nodes like number 1 and number 2, they have children. In such a case, we don't keep data inside of it. We have no data. We just want them to keep the relation. Who is left node, who is the right node, things like that. But we don't expect nodes like 1 or 2 to have data. So if we use struct, we would need, this is 8 bytes. One pointer is 8 bytes. Second one, we need 8 bytes. And data is a double data, so we need 16 bytes. So if we use struct, you can see no matter it's the nodes such as number 1, it will having 32 bytes to denote it. And if we look at a 16, the leaf node, it also needs 32 bytes to denote it. But if we draw that diagram, you will see what is the problem. So if we draw the node 1, if we look at it, it will be a pointer to 2, and it will also, second one will be pointer to 3, but the data part is just wasted, right? If we look at 16, now let's draw the diagram, and you can see here, so for 16, we put some data inside of it. So we use the data, but at 16, it doesn't have the left child and doesn't have the right child, so the space has been wasted. This example just to show us if we use struct data structure to denote such nodes, we would, if the nodes are leaf, then we would have this left pointer, right pointer wasted. If this node is having children, then the data part is wasted. So anyway, we would waste half of the space, right? So if we use struct, we waste half of the space. This is quite inefficient. One way we can deal with this problem is we can use union. For the union, if we declare in such a way, for the union, one good thing about it is we can either interpret the space to be the pointers, or we interpret the space to be data. So if we use the union, still we look at number 1. Right now we have the space like this, and we just want to interpret this space to be pointers. If we have node 16, we still have the same space. Right now, we just want to interpret this space to be data. And if you look at the size of this union, it is 16 bytes. So we would just need 16 bytes to denote node 1, and another 16 bytes to denote the node 16. So you can see the difference. Here we need 32 bytes to denote a node, no matter it's a node having children or not. Here we just need 16 bytes. So we save half of the space when we use union. Okay, do you have any questions? Let me read the chat window. Yeah, that's interesting. That's funny. Okay, do you have any questions? In such way, we can save half of the space. But there's one minor issue. That is when we give you 16 bytes. There's 16 bytes. If I give you 16 bytes, should I interpret this 16 bytes to be a pointer, or should I interpret this space to be data? So which way? Suppose right now we feed this space to a function, and the function would have no idea how it should interpret this space. Either does the space have children and interpret as a pointer, or should we it's a leaf and we interpret it as data. So a function or others won't know what's going on inside, how we should interpret it. So we need to improve our design a little bit. We need to add a type which trying to denote what type of this kind of node. It can be either a leaf or it could be internal. Internal means have children. So we can introduce a type part to specify which type we try to denote. And then anyone look at this space could look at the type and decide how to interpret it. And with it, we use struct. There is struct. We use struct to make this type along with this union. And here, union again, it can be either the pointers or either the data. So in such a way, we can specify a node using 20 bytes. A type is 4 bytes, so we can have 20 bytes to denote one node. And also at the same time, we are able to tell whether this node is leaf or internal. This is the union. Yeah, that's one scenario. Union could be superior than struct, and this is how we use it. Is there any questions? Here we will talk about one thing. It's called data alignment. We will tackle this issue, why we have blank space in between. There's a blank space. You see we have some blank space. And now we will talk about why we have it and how large is the white space. And before we talk about why, let's just look at a real world example. This is just the C program I read about. For this struct, I have one integer, one char, another integer. And if we look at the assembly, let's see how they are organized. So first of all, we can find that the I part is the RBP minus 12, that is denoting I, and next one, RBP minus 8, that is denoting the char C, and the RBP minus 4, that is J. So if we draw the diagram, we can find what does that look like. So if we draw a diagram, let's assume right now here is each slot is 1 byte. Let's say this is RBP minus 12. You can see here we use there should be RBP minus 8, and there should be RBP minus 4. If you look at the space, we will use RBP minus 12 to hold I. So here is the I. And we also see RBP minus 8 is C, and the RBP minus 4 is J. And you can see here anything in between that is empty. So here is empty, empty, empty. Okay, so the real world example just shows you there's empty space between C and J. And now let's talk about why we have these empty spaces. That is called the data alignment principle. The data alignment principle is a principle that any primitive object, let's assume the size of this object is k bytes, and then it requests the addresses, the address to hold this object is a multiple of k. Let's give you an example. Let's assume this object is an integer, and the size of the integer is 4 bytes. And for this 4 bytes integer, the address to hold this integer should be multiple of 4. So we can talk about the example. If the address is 4, it is allowed to keep this integer. If it is 6, no, 6 is not a multiple of 4, so 6 cannot hold the integer. 8, again, able to hold the integer. If we take this look, it will be more clear. So if we talk about char, this yellow is a char. We need to make sure the starting address of it, 268, is a multiple of 1. Apparently, any address satisfying it. If we look at short, for short, we have 2 bytes. And for these 2 bytes, the starting address of the 2 bytes should be multiple of 2. So 0 could be, 4 is satisfying, but not 3, not 5, not 7, right? So we cannot have 3 or 4 to hold a short. It's not allowed. So we need to find an address which is multiple of 2. And here is the integer. For the integer, we have 4 bytes. That means the address of this integer should be multiple of 4. So 0 can be, 8 can be, but not 6. Not 6. 4 is okay. That's called a data alignment requirement. Is there any questions? And actually, I can give you a live demo and show you that is the case in our C programming. Let me open my terminal. A question from John Michael. So for the short, 2 can be an example of it as well. Yes, for short, the address 2 is satisfying the data alignment. Now I'm trying to open my terminal and show you something. Okay, so let's right now just write down a program, test program. let's see, integer A, char C, integer B, and then we printf the size of S1 is if we write down a C program like this, you can see the size of S1 is 12. Go back here. You can see here, we simply write down struct A, C, and B, and we look at what is the size of the S1. So here's a quick program to print out the size of struct. And if we don't know data alignment, we probably would calculate in this way. A is 4 bytes, char is 1 byte, another B is 4 bytes. It should be 9 bytes. But if we look at the printout, it is 12 bytes. So there's a 3 extra bytes than we would expect. The reason is because it's data alignments. And the reason is about the data alignments. There's question from Brandon. If you change the order of C and B, then it would be 9 bytes, correct? That's a good question. We can try. Test.c, if we make change the order of it. GCC test.c. It's still 12 bytes. Okay, that's something surprising, right? Let's talk about why. Now let's start, first of all, let's just assume the easier case. Why the size of the struct is 12 bytes. Here's a case. Integer I, char C, integer J. So apparently the layout of the memory is not like this. We need to modify that. And how we can come up with 12 bytes. So let's look at the first element, integer I. Let's assume it's starting from address 0, right? And from here, we can see 0 is a multiple of 4. So the integer I, this is integer I, it's fine. Okay. And when we do the second part, we look at the char C, and it's just 1 byte, and any address is a multiple of 1. So 4, this is the address at address 4, it is a char, and it should be right. It doesn't matter. But the problem comes when we want to look at integer J. For integer J, number 5, the address 5 is not a multiple of 4. So we need to skip 5. 5 cannot be a good address to hold integer J. How about 6? No, it's not a multiple of 4. 7, not as well, until we find 8. So from 8, we start to hold J. And by doing so, by satisfying the data alignment, you see here, we need 3 empty spaces between C and J in order to make sure J has a good starting address. That's the reason why we try to look at the size of this struct. It will give you 12 bytes because of the data alignment requirement. Is there any questions? A question would from Aaron. So make one of the variables a double, then we would struct take 24 bytes. Let's do a calculation. Now, if we make this integer j, if we substitute it to be double j, double is 8 bytes. It seems like this 8 bytes, this 8 is fine. So probably we would have 4 bytes plus another 4 bytes plus 8 bytes. It should be 16 bytes for the struct instead of 24. Because starting from address 8, we can hold a double variable, and the double variable would it be 8 bytes. So the total size of it would be 16 bytes. Is that clear, Aaron? Okay, great. So the next question is, would an integer char takes 9 bytes? That's a good one. And now let's tackle the issue. In our demo, we just show that even we have the integer ij with char c followed, the size of it is still 12. There's a case. It is still 12. Why? So the reason is when we do the first one, everything is satisfied. So 0 is multiple of 4, 4 is multiple of 4, and 8 is multiple of 1. Everything looks good. Until we define something like array of this struct. If we define the array of this struct, we would have the following one to be from 9, we need to put down another integer I. So integer I, from 9 to 12, we need to put I. It's apparent that the next element in this array wouldn't satisfy the data alignment. So that's a problem. So we cannot start from 9. And how we can do that, we need to insert space here, still gray area, right here, until 12. From 12, that's a good place we start to place the I. So that's the reason we still need gray spaces after the char, so that try to make the next element of substruct satisfying the data alignment automatically. So that's the reason even we change the order, have the integer I, integer j, and the char c, we still insert blank space afterwards because we're trying to accommodate the next element of the struct if we have. So that's the reason is to have okay. Is that clear? Why we change the order? We still have 12 bytes. Okay, great. So for our data alignment, if we do some exercise like that, first thing we need to make sure for the current structure, we need to make sure every item to be happy with your address. That's the first thing to check about. The second thing, we can imagine we have an array of such structures. We have an array of them. And how about the first one first element, it happy about the addresses. How about the second one? So we need to go beyond and think about the shoes of array and make sure the next element is also happy with the addresses. This is two-step check, and if you do these two steps, you could correctly figure out the size of one struct. Um, in the data alignment is underlying reason why we insert blank spaces, because we cannot start from the blank spaces. We have to postpone to find a good addresses to start. Okay, this is data alignment. Now let's do some exercises. These exercises, we would try to look at what is the size for each struct. Now let's first look at the first one. For this struct S1, we have one integer, one char, and the union. And this union, inside of it, we have an integer, we have a char, and now we want to know what should be the size of S1. So apparently, to solve this problem, you need to know what is the union, and what's the difference from the struct. And secondly, you need to consider the data alignment. And I will give you 3 minutes. You can think about and what should be the size of this struct. And if you have questions, feel free to ask. Okay, you can have a paper and draw the memory map and see what should be the right size of it. Okay, let's do it together. So first of all, let's check what should be the right answer. So here, let's do, I just copy the code from the slides to the C program, and we have struct. I just copy everything, and now I'll just look at what should be the size of S. Compile it, and the size of S1 is 12. So 12 is the right answer. Let's look back why it is 12. So first of all, let's just draw the memory right here. Let's just assume the address starts with 0. I will from 0. Okay. 0, and it's okay that 0 is the address to hold I. So 0 into 3, we use that to store I. Store A. That's not a problem. Integer A is 4 bytes, and the 0 is a multiple of 4. So we can figure out, A. Next part, we need to have a char. So we come 4, and then here, char is no problem. This is char B. And the next part, this is a little bit more complicated. So very first, we need to figure out what is the size for this union. Size of this union should be determined by the larger one. Integer of A is 4 bytes, char B is 1 byte. So we need to make sure that this union have space 4 bytes. So union would have the size of 4 bytes. This object, 4 bytes. And for 4 bytes, if we look at 5, it is not a multiple of 4, 6 not, 7 not. So we need to start from 8. We start to have this union. So union is one object, and the size of union is 4 bytes, and so that the starting address of it should be multiple of 4. So we should put that to be the union U1. And we can look beyond such a current element. If we build an array of it, the next one, if we want to start the next element, the starting address is 12. That should be fine. So this will be the size of it. And the 5, 6, 7 would be left blank, and the total size of it is 12. Okay, that's why this structure would have 12. Is there any questions? Okay, if you don't have questions, let's do a summary. So we don't have time to do the second one. We would do an exercise next lecture at the beginning. We will do the second one. But right now, let's do a quick summary about today's contents. So today we talk about struct. For struct, it's not so much difference from array. The only difference is struct, each item could be having different sizes. So in order to figure out the address for each item, we need to manually calculate the addresses. That's the only difference from the array. Because the size for each item is maybe different, so there's no way we come up with a mathematical equation to do that. For the struct, we talk about one example. What does assembly code look like if we walk through one linked list? And this is a typical assembly code you would see. And we also talk about union. Union is very similar with struct from the papers, but internally it's quite different. For the struct, all the items are coexisting with each other. They all exist. But for union, all the items are just possible choices. We just have one common space. Either we interpret the common space to be the first item, or the second, or the third. No matter how many you have, you can just choose one item. And the size of this union is determined by the largest item possible. Example, here is the largest possible is 8 bytes, then union should have 8 bytes. And we just interpret this union to be either cases at one time, but they cannot coexist. And we give example, sometimes union could be superior than struct. In this example, we have nodes, we have the internal nodes, we have the leaf nodes, even though they are called nodes, but they are different. In such a case, if we use struct, we would waste half of the space. But if we change that to be the union, we either interpret the space to be the pointers or interpret the space to hold data, but not always, not true for both. So that actually quite an efficient way for our case if we declare that to be union. By this way, we save the half wasted space. And one minor issue is if we hand this space to a function, there's no way to tell whether we should interpret space to be pointers or data. So we need one extra type which exists all the time to tell us what type of this node is. In the second part of our lecture, we're trying to talk about data alignment. For the data alignment, we hope to, when we have an object K, we need the address of this object is a multiple of K. This data alignment requirement is the reason that when we mirror the size of this struct, it will give you 12 because for the last item J, we need to find a good address to start. So we have to leave 3 blank spaces in between so as to accommodate integer J. That's the reason if we mirror the size of this struct, it will give you 12 instead of 9. Okay, that will be our today's contents. And if you have questions, I will be around. And thank you for attending.